All right, so I am going to talk about adaptive control application to distributed control of modular systems. But, so this presentation contributes to both modular systems. I'm going to explain. It is a class of large-scale systems, but also it contributes to adaptive control as well. So it has two contributions, which I am going to highlight. So first, I don't know what's going on with this slide, but let me proceed. This is a similar slide from this morning. Basically, for a single system, it was hard to model because of the idealized assumptions, model simplifications. We had a lot of uncertainty. But modular systems basically composed of several subsystems that they interact with each other. You can think, for example, a simplest modular system is, let's say you have two inverted pendulums, and I am going to connect those inverted pendulums to each other by, for example, a spring. So the motion in one inverted pendulum affects the other inverted pendulum. So it is a modular system, and for example, you can model tall buildings, space structures like that. So it is a large-scale modular system such that subsystems interact with each other, such that for one system, modeling is costly, and we are doing a lot of assumptions. And for the entire system, of course, we do have uncertainty. And so we need to design a distributed control such that each local subsystem has its own controller such that it achieves a global performance in the presence of uncertainties. So I already talked about this slide, just back up a little bit. So why adaptive control? Because we compared adaptive control with robust controllers or fixed gain controllers, and since they are tuned to a worst case, not to a physical system, and since they cannot improve themselves, we highlighted the advantages of using adaptive controllers. And for example, I have a new example here. Let's say we have a spring mass damper system. For robust control, we are assuming that, for example, let's say mass is between 1 or 1.2 kilograms. But what happens if really mass is 0.8 kilograms? So we need adaptive control to adapt to this condition. And it is evident that after so many talks today, we need adaptive controllers since they tune themselves to the physical system to achieve some desired properties. Now, here is the design challenge. And worst case performance bounds in adaptive control depends on the uncertainty. So if you talk about verification validation of adaptive controllers, you need to meaningfully talk about your worst case bounds. But in the derivations that I showed before, Travis showed, Naira showed, so on and so forth, these worst case L infinity bounds depend on the uncertainty. So if you would like to know these bounds, you need to know a conservative upper bound on the uncertainty. Otherwise, if you don't know the uncertainty, you cannot compute those bounds. And another design challenge, control engineers cannot assign a priori bounds without knowing the uncertainty during a design. For example, I would like to do this. I am employing an adaptive control, and I would like to assign, for example, my error bound, my error will not exceed some epsilon. And I would like to give them epsilon at the beginning of the slide, so that at the beginning of the design, so that I would like to be confident that my adaptive control always behaves in this bound and never exceeds that bound. And if we cannot do that, especially for modular systems, this design issue can lead to a modular system failure. For example, let's look at this by the Cortes of San Diego, like this tall building. Let's say we have each local adaptive controllers in each local system, and let's say this goes to the right by 1 foot, this goes to 1 foot, 1 foot, 1 foot, then this fails. So I would like to assign that entire system will not go to left or right to any direction by more than epsilon, and I would like to assign that epsilon during the design. So it is a challenge. Now, this was the adaptive control challenge. Now, let me also review literature a little bit on distributed adaptation, and all these references are included on your flash drives. So the traditional approaches considers this figure A. So I have a local subsystem. This thick line is the hard connection like springs, dampers to the other system. And these thin lines are the software connections between virtual connections between subsystem and the controller. So traditional approaches assumes that every system communicates with its local subsystem and they don't communicate with others. So since this is the case, since no communication is allowed, no asymptotic stability result can be achieved. More recent approaches consider control exchange. For example, okay, let's say I have a lot of local subsystems. They don't communicate with each other, but every local controller accesses to the desired trajectories of all others. This is proposed by Narendra, and this is okay, but of course, there is a cost of communication, and really the question is, does every local controller, do they need to communicate with others all the time? Probably not. I only need to communicate with my neighbors modeled on a graph, which is the contribution of this presentation. And other approaches, also there are approaches like, okay, let's say controllers doesn't communicate with each other, but every local system once in a while exchange their state information with all others. And still, again, the same question, do they need to exchange all information with each other? Probably not. Again, cost of communication. But allowing communication is the novelty of these approaches, such that you can achieve asymptotic stability in the context of adaptive controls. Still, we cannot have a prior performance guarantees, but this is not the problem of these approaches. Performance guarantees is the problem of the adaptive control field. So basically, in this presentation, I will allow all local systems just to communicate with their neighbors. So if I am connected to Travis, I would like to get Travis's information, but I don't need to get all information from you because I am hardly connected to Travis, but I am not connected to you. If Travis is connected to you, then he may need your information. So we are modeled in a graph. In this example, we have a circular graph. Now, through hard connections, my uncertainty affects my neighbors, and my neighbors' uncertainty affects me, and I exchange my software controller with my controller, and I also exchange a part of my state information with my neighbors. Now, here is the more mathematical modular systems formulation. A modular system consists of n uncertain heterogeneous, they are not identical. Think, for example, a spacecraft, submodules defined on a graph, such that the physical interactions between submodules are known. So for example, let's say this is the local subsystem. We have, in this case, we are introducing these I subscripts because we have n subsystems. We have AI xi is known to that local subsystem. BI UI is the control of that local subsystem, modular system, and this is the uncertainty of that local system, and this is the uncertainty coming from my neighbors, and this is the uncertainty, my individual uncertainty of that system. This is through the interconnections, hard interconnections. And assumptions are the first and second assumption, actually three assumptions are standard, basically saying there exists a parameterization of the uncertainty and there exists known basis functions. So here is the problem, allowing local, not global. I don't need to exchange my information with all of you. I just need to exchange my information with my neighbors. So the problem is allowing local communication through graph. Each local submodule has to follow desired trajectories captured by these heterogeneous reference models of each individual subsystem with a priori assigned prescribed performance bounds. This first part contributes to the large-scale system, and second part contributes to adaptive control. And we have standard matching conditions on each heterogeneous local subsystem. Now, here is the distributed adaptive control. Here we are grouping the uncertain terms with the local controller. So here I am denoting this to be u tilde. U tilde is a large function. Here I am assuming that there is no nominal controller. Of course, you can consider augmenting scheme. So here is everything is unknown, but UI is known. This is your local control system, control signal. So let's, these terms look really ugly, but I can write this, I can define Wi transpose multiplied by sigma to be all these uncertainties, but Wi is a giant unknown matrix, and this is basis function composed of my state, my neighbor state, local neighbor state, and the comment that is applied to my local subsystem only. Well, here is the, we are revisiting traditional adaptive control application of this modular system. EI dot equals to ARE AI minus this uncertain term. So if we, instead of choosing one Lyapunov function here, if you choose for n subsystems, if you choose n Lyapunov functions, then you can have V dot is upper bounded is equal to minus of this EI transpose RI EI, which is kind of an expected result. And hence, by using Barbalat's, error goes to 0, the difference between each system and each the reference models, if we use this weight update law. So here, this result shows that by allowing local communications, basically without requiring global communications like the other papers, we can achieve stability, asymptotic stability on the error. So that's the first contribution of this paper, this result, which contributes to, again, modular systems, not to adaptive control, because adaptive control-wise, we are just using standard traditional adaptive control to solve a problem. So up to this point, it is an interesting application of adaptive control to modular systems by allowing local subsystem communications. Now, before talking about the adaptive control contribution, let's talk about this. So for single systems, we discussed, achieving performance is important, but for modular systems, it is absolutely important because every deviation from a desired performance in each local subsystem can propagate through the entire system. Then it can destabilize the entire system. So during the transit, and we need to have guaranteed bonds to achieve this. Let's say we can assume, let's say for discussion, let's say initial error mismatch is 0. So traditional setup enforces to use high gain all the time if we would like to achieve strict performance guarantees, which means it uses the available system bandwidth all the time, which is not desired to use high gain. And to compute, otherwise, you may not need to resort to high gain. So, but if you are interested in computing this, first of all, very conservative L infinity bound, you need to know this uncertainty. So either you would like to compute it or you need to use high gain if you would like to, if you are interested in achieving harsh guarantees, very strict guarantees on the performance. Now, of course, this can cause oscillations, but you can employ, for example, low frequency learning or closed reference model, so on and so forth. But my point is, you still need to use know W to compute these worst case bounds. Now, instead of using high gain all the time, we would like to use high gain only when it is absolutely necessary. So for this, I am going to introduce a new set-theoretic adaptive control approach. Basically here, you will see that it will be a state-dependent rate adjustment approach for the learning rate, such that we can achieve a priori known system performance. So let me introduce restricted potential functions, phi. So here, Z is a H norm, which is defined like this. So basically, this Z is defined on an interval between 0 and epsilon is not included. So this Z of H norm is belonging to a set from 0 to epsilon. And you will see that this epsilon will be your design parameter eventually. So I'm going to talk about it in a second. But this phi satisfies 5 properties. And these are not assumptions on the system, but these are your design assumptions. So basically, you need to choose a phi that satisfies all these 5 conditions. So first condition is if z is h norm of z is 0, then this phi is 0. Okay, this is straightforward. The second one is if z of h is in this epsilon domain, and if z is not 0, then phi, your restricted potential function, needs to be positive. And by the way, it is a scalar function. And if z is approaching the epsilon, then this phi approaches the infinity. And this phi is continuously differentiable on that domain. Outside that domain, I don't care. The final one, if z is on that domain, and if derivative of phi, here derivative with respect to z h norm square, if it is on that domain, then its derivative needs to be positive. So here is a function, a candidate restrictive potential function that's satisfying all these conditions, which I am going to use this in the examples. Now, this black line shows that this phi, and the other one shows its time derivative. And here, this is plotted for epsilon equals to 4. So a candidate local function that satisfies all the properties. So now stability with explicit performance guarantees. I am going to consider this restricted Lyapunov function. Here is the restricted potential function plus the conventional stuff for the weight estimation error. And here, I am defining this Lyapunov function not in the entire domain. I am defining it to be d of ai that you design by choosing this epsilon multiplied by, this is defined on the r dimension w tilde, and it is defined, it is positive definite. And basically, using this derivative, which you can write it like that, you can have v dot of I equals to this derivative of this restricted potential function, which is a positive quantity, multiplied by ei transpose ri and ei. And if and only if you can choose this weight update law. Now, this weight update law looks like a standard weight update law. So you can apply all the modifications or all the approaches that we discussed today to get rid of oscillations or so on and so forth. But the novelty of it, it has this derivative of this restricted potential function such that even you can get rid of this gamma I, you can set it to 1 and see how the algorithm works. And basically, it will tune this algorithm in such a way that this system trajectories will always stay in this compact and invariant set. And ei goes to 0 as t goes to infinity follows from LaSalle-Yushizova theorem or Balbas. Now, error trajectory always stays here inside user-defined bounds, because I choose my Lyapunov function like that on this DE domain, such that I need to come up with epsilon, and then my error trajectory will stay on that epsilon. This is a design parameter. This is not an analysis parameter. And the proposed setup enforces to use high gain, because of, if you look at this function, if the error is large, then you may need to resort to high gain. But in contrast to standard adaptive control, it uses high gain only when it is absolutely necessary. For example, let's say you are at a critical angle of attack and you don't know how to control the system, then adaptive control enforces high gain to come back to original aircraft settings. So it uses high gain only when it is absolutely necessary. And of course, using high gain all the time, it is not desired. Now, I am considering this example. Basically, we have 8 couple of inverted pendulums, and like this, they are connected with each other's dampers and springs. These are non-identical springs and dampers, and they are unknown. And torque generated by each pendulum motor is subject to uncertain and heterogeneous control effectiveness. So I don't know how well my torques of my inverted pendulums generate those torques. So everything about this system is uncertain, plus I am not having a nominal controller. So this satisfies matching conditions that we discussed, and I'm going to turn on the adaptive controller to see what happens. So here is the illustrative example. I am only going to plot these angles of these inverted pendulums with the reference model pendulums. So basically this dashed line is the reference model trajectories of each pendulum, and the reason I choose them to be the same because this is it is easier to construct that plot. You can certainly choose 8 different reference model phi for each pendulum, but then this plot will be hard to explain. So that's the only reason I choose the same. And the code is on your flash drives, and you can feel free to play with the code, certainly. And basically, it tracks well, and this is the control signal. We have a little bit of oscillations here because this paper is not transient performance. You can certainly employ low frequency learning or open loop reference models, so on and so forth, to improve transients. This is not the scope of these presentations, but the scope is this: every inverted pendulum trajectory stays within this epsilon equals to 1. Errors never exceed 1 because this is the design that I am for. So here, at the beginning of the design, I choose this epsilon to be 1 on that restrictive potential function that you see here, and instead of z, basically I used e, error. And basically it stays between prescribed bounds, and it converges to error converges to 0 asymptotically. So one Lyapunov function and 2 objectives, not only stability but also worst case, a prior known user assigned worst case bounds that do not depend on the uncertainty in the system. And here is the how effective learning rate adaptation gain behaves. Here system trajectory is approaching to this epsilon, then adaptation gain becomes large, which is kind of expected. But for the rest, adaptation gain is extremely small because we don't need to use adaptation control around these regions. So algorithm decides what adaptation gain to use to achieve some prescribed bound. And so that's how it works. So basically, concluding remarks are, this has 2 contributions. The first contribution is the modular systems, how to achieve asymptotic stability via not global communications, but local communications that are only graph-theoretically modeled. And contribution to adaptive control is uncertainty independent performance bounds determined by control engineers, and which is important from the verification and validation point of view. And ongoing research, first I will read this. If bounds on the user-defined functions are extremely tight, and that exists significant amount of measurement noise in states, then adaptation gains, yes, very large. And in this case, you need to use a smoothing functions, or you need to limit. For example, in this theory, you need to have, for example, if your software limit in the high adaptation gain is 1000, then this should not be go to infinity, but this should be limited at 1000. In this case, you can talk about, of course, approximate enforcement of this constraint on the error dynamics. Which actually I suggest to do if you would like to have very tight bounds and excessive amount of measurement noise. And another approach is to limit frequency content to achieve robustness. In this case, if you have measurement noise, then you need to use low frequency, for example, to get rid of that your adaptive control will not see that high frequency or unmodeled dynamics and so on and so forth, so that you can confidently use that algorithm. Second extension is incorporating state constraints with control constraints. which is kind of a harder problem, which actually we are trying to address. This talks about error, or in some sense, state constraints, because if you limit error constraints, then it eventually limits the state constraints. So how you can do both simultaneously. And also consideration of communication dropouts, event triggers, or time delays in the communication between submodules. And here is my collaborator from Georgia Tech, Jeff Shama, and I would like to take your questions.
I have a question.
Sure.
It's related to the state and control constraints. Right? So all the presentations that we've heard today, no one really talked about those constraints. So
control constraints? Yeah. That's right. Usually.
And so do all the proofs and all the theoreticals fall apart when you have that?
I personally like, for control constraints, I personally like using a method introduced at Georgia Tech by Eric Johnson and Anthony Callis, so-called pseudo-control hedging. And in fact, it is indeed included in your flash drives. So it is an important problem. So we try to include every aspect in adaptive control, even though it is not covered in here. Also, you will see a couple of papers that talks about neural networks, because if you don't know the basis function, then you need to approximate it by using universal approximation tools like neural networks. But we try to consider here more fundamental approaches, but they are doable, and they are in your flash drives, and you should certainly check those. And if you have any questions, I mean, regarding neuroadaptive control, almost everyone has experience in this. You can either email to either one of us.
For input constraint, yeah, there's basically 3 or 4. So they all go back. I mean, everyone has one. So Anu did one where you just subtract out the difference. So I guess at the same time that Eric Johnson did his work, Naira, Qingyu, and Eugene